Let's look at what would happen if I send a continuous wave, right, a sine wave, from both sides of the medium. So one wave, they have the same amplitude, they have the same wavelength, they have the same speed, but the velocity is different because one is going to the right, to your left, and the other one is going to the right. Right? So what this plot is showing is, in black, you see the sum. This is what the medium, the string in this case, is doing as these two waves are moving. So you wouldn't really see the blue and the red one. What you would see is just the black dots. Okay? But we constructed this wave by sending a continuous train of wave from the left. That will be the red one. You see it here. It's moving to the right. That's the red color. And there is a blue one moving continuously with the same speed as the waves do to the left. That's the blue one. Right? And when those two waves move in the same medium, they produce the pattern that you see with black. At this time, the two waves are overlapping each other, right? The blue is right on top of the red one. Let's think about what's happening to the phase of each one of these waves at the point that is marked with N. You already know that that N stands for node and the A stands for antinode, right? So let's look at a node and see if we can understand why there seems to be these points. Node, for example, this one that doesn't seem to move at all. At any time, it doesn't move. If you pay attention to that, you see that that point, we're looking at the black wave, right? This seems to be pinned to this location. This one is not moving at all. This one is not moving at all. And in between those two nodes, you find this node where the rope is oscillating with its maximum amplitude, right? Going all the way positive, negative, and so on. So let's look at the node and see what the phase of the waves are at that point. I have selected my origin of coordinates. This is x, and this is displacement. I'm using the notation in the book that uses d, right, for the wave, d of x and t, right? And the previous class I was talking about delta y. Delta y makes sense for a transverse wave, where you're talking about the height, right, of every point. The notation d is better because it applies for both transverse wave and longitudinal wave. This just means the displacement from the equilibrium point. If you're talking about a longitudinal wave, the displacement from the equilibrium point happens in the direction of the wave, right? That would be your d. It's a function of position and time. But if it's a transverse wave, like in a rope, then the displacement that you're talking about is the height above the equilibrium. Just side note there. So this is the red wave that you see there. And the red wave is moving to the right. And on top of that one, at this instant of time, they coincide. So on top of that one, I have the blue one. But the blue one is moving that way, right? I'm going to look at the phase of this point. which we call a node, right? So I'm going to do my little circle here and draw the little vectors, the phasors corresponding to the phase of one of the waves at that point, at that time, and the phase of the other wave. So let's say for the red one, what's the phase of the wave at that point? If this is the origin and say that this is t equals 0. At t equals 0, I started my stopwatch, and this is what I have at t equals 0. The two waves are overlapping at that point. They're overlapping at this time, t equals 0. So what's the phase of the blue wave? How do I write the displacement of a wave as a function of the wave? That's it, right? And the phase is a function of position, and it's a function of time, and it's a function that can be plus or minus omega t, and there might be some initial phase here. The way I chose t equals 0 and my origin, I'm just getting rid of this term. There's no initial phase there. It's 0 basically. So the phase is that angle, right? The function that you're looking at is a sine function, and at that point, what is the angle? What is the argument of the sine function at this point? At this point, this is equal to what? D is equal to what? 0. Therefore, the phase is equal to either 0 or pi. I know it's got to be 0 because the function, the displacement, grows as you move that way. As the phase increases, the displacement increases. That is consistent with a phase being equal to 0, because that's what a sine of an angle does. This is phi, and this is sine of phi. At phi equals 0, sine of phi moves like this. It goes up, right? At phi equal pi, sine of phi goes down if you increase the phase. Okay? When I move that way in x, the phase always increases. It's depending on kx. If x increases, kx increases, the phase increases. So I know that at this point, the phase of the wave has to be equal to 0, right? So phi is equal to 0 for both the blue and the red one. Blue wave phasor pointing that way, red wave phasor pointing that way. There's no difference in the phase of those two waves. They look exactly the same. At the t equals 0, they're overlapping. But what's the difference in how those phasors are going to behave as time goes on? If I just stay here, right, and the phasor is my watch, for one wave, the phasor moves in the way the watch would move, which is clockwise. Right? That's for the wave that has the negative sign, which is the right? The red one, the equation for the red one is displacement of the red one is a sine of kx minus omega t. The displacement for the blue one is a sine of kx plus omega t. Okay? So for the red one, as time goes on, your angle, your phase decreases. Right? That means that the phasor moves down clockwise. Because remember that angles are measured increase in the counterclockwise direction. That's our usual standard for measuring angles. Positive going this way, negative going that way. Right? The red wave has a minus omega t, which means that if you're sitting at one particular point, and suppose that my watch was the phase of that wave at that point, the phase would be moving as the handles move. Okay? So this way. But that's not what the blue one does. If a wave moving to the left has an equation that has with that goes with a plus omega t. Okay? So at that same point, the little handles describing it, how does the phase move with, or change with respect to time, that handle goes in the opposite direction. Because as time goes on, omega t adds up to the phase. It doesn't subtract, it adds up to the phase. So whatever the phase was at a certain time, if you let time go by even more, pass by even more, then it adds to it. It adds phase with omega t, as a omega t. Okay? So notice that those two phasors are moving in opposite directions. One is going down. I'm going to try to do that with my hands. The red one is going down, the blue one is going up. Right? And they keep spinning, one in one direction, the other in the opposite direction. Right? So sometime later, how does it look like? Sometime later, the blue one, which is spinning this way with omega t, is going to be pointing this way. And the red one, which is spinning in the opposite direction, is going to be pointing this way. And if you add those two vectors, you get a resultant vector, which points along the x-axis. Okay? That tells you that the displacement of that oscillator is 0. It does not move. Right? The displacement due to each one of those waves is canceling the displacement of the other wave. When one is trying to get the rope to get a positive displacement, the other wave at the same time is trying to get the wave to get negative displacement. Right? This is the displacement. The y component of this vector is what you call your d. Right? This will be your d2, is this, the y component of that. The y component of this vector is what we call d1, as I specify there. Okay? So at this particular point, one wave is telling the rope to go up, the other wave is telling the rope to go down. They're telling the wave to do that with the same strength. Those two behaviors cancel each other completely at all times. Okay? So the only thing that the resulting phasor does is it can grow and then shrink and then point in the opposite direction and then shrink and then point in the opposite direction, but it never spins around. And because it's always on the x-axis, that means that the displacement associated with that is 0. Okay? Whatever oscillator you have at that point, that oscillator will not move. So that is a node. Can do the same thing and look at a different point. Let's say this point over here. One blue, one red. The x-axis, that's the displacement. The superposition, what you actually see happen in that wave is what we said, the black one, which would be a curve like that one, but just bigger amplitude, right? Okay, so this is at t equals 0. Let's look at this point. This point has a phase. Two waves there, so we're going to draw a vector for each one of those waves. Once again, what's the phase of the wave at this point? I over 2, right? So, and for both of them. So the blue phasor and the red one are pointing in the same direction at that point. what happens as time goes on. We already discussed the behavior of the blue one and the red one in terms of as time goes on, which one each one goes. So the blue one goes this way, and the red one goes that way. So sometime later, you will find the blue phasor pointing this way, and the red one pointing this way. Notice that at all times, they have the same displacement. They are prompting the rope to have the same displacement, right? Because of the symmetry. At this point, they're pointing in the same direction, and they move away from that direction with the same angular frequency omega. So at all times, you would expect them to have matching displacements. So when they're pointing this way or that way, they still have the same displacement. So what does that tell you? That tells you that the net displacement of that oscillator at this point is going to be pretty big when they're aligned, right? It's going to be a little less. It's going to be 0 when the two vectors are pointing like that way. Then it's going to start growing negative as the vectors approach the vertical in the negative direction. It's going to be maximum negative when the two vectors are aligned here. So what that tells you about the oscillation of this point is that it's going to be moving from maximum amplitude at positive over here all the way to negative, all the way to positive, and so on. So that's a point that is going to have a maximum amplitude of oscillation, right? Those are the points that we call antinodes. Again, the important or the characteristic of that point is that the two waves that are interfering at that point, they produce the same displacement on the medium, same displacement at all times. One is doing positive, the other one is doing positive, so they reinforce each other. The node one is trying to make it go up, the other one's trying to make it go down, so they cancel each other out. You can do this mathematically, of course. D1 is a sine of, let me be consistent with what I wrote before. I call D1 the one with the minus. D1 is kx minus omega t. D2, the second wave, is, this is the one moving to the right, this one's going to the left. Kx plus omega t. And the displacement of the rope, and this is the main idea of this chapter, which is when you have two waves, you add, algebraically, you add the displacement due to each one of the waves. This is the main idea, how waves behave. So then you have this a sine of kx minus omega t plus a sine of kx plus omega t. You can split this, the sine of alpha minus beta or alpha plus beta, with the sine of alpha, cosine beta, and so on. I won't go through all the steps, but this is the answer. It's just two more steps. It's 2a sine of kx cosine omega t. That thing is called a standing wave. Why do we call it a standing wave? Yeah. Right, just like you saw in there. The black, which is the wave, the resulting of the blue and the red one, that's the D1 plus D2 after you add them. This is what you get. It doesn't seem, this peak, if you follow it, it just goes up and down. It doesn't seem to be moving to the right or to the left. That is consistent with what we talked about, the phasors. The phasor in either for the node or the antinode, they result in when you add the blue one with the red one, right? What you get is, in the antinode case, you get a phasor that is pointing vertical, shrinks, goes negative, goes up, goes down. It does not spin anymore. Okay? If it doesn't spin anymore, it's not a traveling wave anymore. traveling wave will have a phase that spins around as time goes on. It can go one way or it can go the other way, and it depends on the position. But a standing wave doesn't have that behavior. Every point on the rope of a standing wave, the phase of that point does not change in time as a kx minus omega t. It doesn't do that anymore. So if I were to take a picture of the standing wave, again with a node at the origin, and if I were to take a picture of that wave half a period later, it will be doing this. This is the usual way a standing wave is represented in the book. They draw this kind of pattern. What it really is showing is not that the wave has at all times is doing these bumps, right? What the wave is doing at any time is doing this. It just looks like a sine wave. It's just that it oscillates like this, right? So people usually draw the maximum displacement on one side and the maximum displacement on the other side. The curve that has that maximum displacement. In between times, this is what the wave will look like. Right? It kind of starts going towards the origin and then it flat, equilibrium, but the velocities are not zero, so it bounces back, it keeps going, in other words, and then it reaches this, and so on. It just keeps going like this. Okay, notice that in the equation that we derive, the displacement for the standing wave is 2a sine of kx cosine omega t. This k, where does that k come from? This is the same k as the k of the two traveling waves that are moving through the medium, right? Remember that d1 was described by a sine of kx minus omega t, and d2 was described by a sine of kx plus omega t. Both waves have the same k, which means they have the same wavelength. They have the same wavelength. So the result that you have here is true for two waves moving in opposite directions with the same amplitude, with the same wavelength. Okay? The omegas, of course, are the same too. Because the medium determines the velocity, the k is related to the velocity and omega, so if they have the same k, they have to have the same omega. So this k is coming from that. It's 2 pi divided by lambda. So when you look at the standing wave, if you take a snapshot of a standing wave, this is what you would see, right? This distance is as it was before, as it would be for just one wave. That distance is lambda. Okay. But what you would see when you do the experiment this week, what you're going to see with your eye, looking at a string that is vibrating that way, is these bumps, right? You would count the number of bumps because it's oscillating sometimes quickly between this and that. So what you end up seeing, it blurs, the image blurs, and you see it's just one blob and another blob and another blob next to it, right? So what you want to count is probably the distance between the antinodes, which is going to be lambda divided by 2. For a standing wave, the distance between two antinodes or between two nodes, it's going to be lambda divided by 2.